Well, it's really a tremendous pleasure and honor to be here, and actually a surprise. If you asked me 10 or 15 years ago whether I'd be giving fancy Chow lectures to a group of distinguished mathematicians, some of you are distinguished for sure. Well, there's one, at least. In Leipzig, I would have thought we were totally nuts. I'm obviously not a mathematician. I'm not even a mathematical physicist. I'm a physicist who loves math. That's not the same thing. But this has happened. 15 years ago, I spent 2 years of my life where my dominant collaborators were experimental particle physicists at the Large Hadron Collider. And somehow it's come to be that I've spent the last 10 years of my life where my dominant collaborators, my most exciting collaborations have been with mathematicians. And this is a reflection of the grandeur of the physical universe and the Platonic mathematical universe and their still mysterious and wonderful connection that it managed to bring these groups of people together. I suspect it would have also been a shock to a combinatorialist or algebraic geometers to think that anything that they're thinking about would have to do with very basic physics, fundamental, very basic processes that happen in the world all the time. Not esoteric questions about the partition function of complicated theory X on complicated manifold Y, but what happens when things are going on in the real world right outside our window. It's remarkable, it's a surprise, and so I'm delighted to be here to be able to say something about what's going on. So indeed, that's what's going on. There's been over the past 15 years, really longer, but from this sort of particular point of view that we're talking about for the past 10 or 15 years, accelerating through to the present, some indication of a deep connection between very basic physics, physics having to do with the scattering of elementary particles, more recently physics having to do with the creation of structure in the universe and cosmology on the one hand, and I would say what seems to me as an outsider, very basic and deep parts of mathematics. And another interesting aspect of this connection is it's not like at least the most stereotypical version of the interaction between math and physics that we learn about in school, in lay history. The stereotypical interaction is either that math is a century ahead of physics. Mathematicians come up with group theory, they come up with differential geometry, and 50 or 100 years later, the physicists find that's exactly what they need in order to make progress in physics. Nor is it the other way around. That's sort of been the situation, I would say, with the interaction between quantum field theory and modern mathematics over the past 40 years, that because physicists, well, namely Edward Witten, but some other physicists also, have an amazing intuition for what the path integral does, that leads to lots of amazing mathematical predictions that then mathematicians have to go try to understand from their own way. So if they're the sort of physicists are ahead in some sense, and the mathematicians are catching up. This has been a different subject. This has been a subject where somehow, again, rather mysteriously, physicists and mathematicians are running into roughly the same structures, roughly simultaneously. And so it's been actually good, not for bureaucratic reasons, so you can say we sit together in the same room and have interdisciplinary conversations, but it's actually useful. It's actually useful to discuss the kind of the same objects being seen from different points of view. And it's been a persistent and wonderful shock to me over and over again in a number of different settings how this has happened. All right, so anyway, that's the topic for these lectures, is tell you something about that. Now, before I proceed, I just want to have a rough idea, just a show of hands. How many people, at least before this morning's lectures, how many people knew what a positive Grassmannian was? Okay, excellent, very good. How many people know what spinor helicity variables are? Okay, fewer. Momentum twisters. Okay. That's good. Okay. So this talk is not going to be targeted at the experts. I'll have some things. I mean, the set of talks is not going to be targeted only at the experts. And I don't have any very fixed. I have a rough set of things that I want to talk about, but it'll be exponentially better to have a real interaction. So stop me to do concrete examples. Anything you want to do, we can slow down arbitrarily and talk about arbitrarily elementary points. I love nothing more than elementary points because I understand them well, so it's enjoyable to explain things I understand well. So please do stop me with the questions about any subject as we're going. Okay, so let me just begin by setting the stage, and I'll then get in a bit to what the lectures are going to be about. But a picture that you've seen a number of times. To at least begin with, we're talking about the very basic physics of elementary particle scattering processes. So we have scattering processes and amplitudes, and their amplitudes. Okay, and the sort of most basic picture is, you might imagine, sort of two particles come in. So there's some in state, something happens, and there's a bunch of out states. And so this first picture, well, looks like what it is. It's an evolution of a process in space and time, right? Things start at minus infinity, something happens, and you measure something at plus infinity. The world is quantum mechanical, so when you prepare exactly the same initial state, something different comes out every time. So we can't calculate, we can't say exactly what happens next, but we can calculate the probabilities for this particular process to happen. The probability of in to out is the mod squared of this amplitude, of a scattering amplitude for in to out. One of the very, very first things that you do in textbooks when you learn this in grad school is already change this formula so that you don't actually have a distinction between who's in and out. So one thing that we say is that we have energy and momentum conservation. So each one of the particles, I'll denote the particle label by A. A will be 1 to the total number of particles involved in the scattering process. And let's say if we're in 4 dimensions, these would be 4 vectors. So these have an energy component and a spatial momentum component. And if the particles have a mass m, these are constrained by this equation. The particles might even have different masses. So that's Einstein's formula for the energy of the particle given its momentum. This is sometimes called the mass shell, because as you can see, in energy momentum space, there's some hyperboloid. Okay, so you have to lie on the hyperboloid in energy momentum space. So this is called being on the mass shell. So the particles are on the mass shell, and we also have energy and momentum conservation. Let me just write it in the small here. That says the sum over the p ins is equal to the sum over the p outs. Okay, well, one of the first things that you learn when thinking about amplitudes is that we can, let me write this up here, we can trade this for a function that only depends democratically on a bunch of p where we don't have to say who's in and out. Okay, so there's a function that's actually an analytic function of an analytic enough function of the momenta, where you just get to decide whether p a 0, if the energy component is less than 0 by conventional, we say it's incoming or outgoing. And if it's bigger than 0, we say it's outgoing. Okay, so right from the start, you actually deal with a completely symmetric function, right? At least we don't make any distinctions between in and out, and you get to decide who's in and who's out by controlling the sign of the energy component. Okay? That's already a non-trivial fact that this is true. This is a statement about what this function looks like. It's analytic enough that you can do an analytic continuation from one set of signs to another set of signs. This is a property that's not obvious. It's called crossing symmetry in quantum field theory. It's not obvious, but it ends up being true. It has very not satisfying proofs. But in any case, we're going to just take it to be true. When you work in perturbation theory, and especially in the simplest tree amplitudes, it's an obvious statement about what the functions look like. There are simple rational functions. This sort of analytic continuation is obvious. But right away, I want you to observe from here something interesting has happened in this is the year 1950, okay? That this idea of the amplitude as a matrix that takes you from the past to the future is already a little bit dissolved, right? So it does not have an interpretation necessarily of an in to out. It's something that has all the particles on an equal footing. Okay, so this is the object that we're going to be talking about, and often we label it by the number of particles participating in the scattering process. Now, one of the famous things in this subject is that the amplitudes are, I'm going to use this thing. So we can, the sort of textbook picture for calculating amplitudes is using Feynman diagrams. Okay, so we draw these pictures. Where again, you know, what's happening, I want to stress this point. Maybe mathematicians will appreciate it more than physicists do, because physicists have just gotten so used to thinking about these pictures. But what's really happening is the experimentalist wakes up in the morning in Geneva, collides a bunch of particles, goes and has their espresso, and comes back in the evening to see what the output of the collisions is. Right? That's what's actually happening. In other words, the measurements are done in some idealized way at infinity. Infinite past and infinite future. If you then ask, what is the story for what happened? How can I come up with a theory that explains what happens? That's when the theoretical physicist comes along and says, you know what's happening? These particles are moving through space and time, and this crashed into that one, and this made this one, and that went that way, and this did that, and this did that. Right? This is a story that theoretical physicists give to give an accounting, a rational accounting, for what the outcome of this process is. Okay? Nobody sees this. Right? None of us are riding along with the proton at the LHC to see what's happening with the quarks and gluons inside the proton as they smash into each other. Okay? But it's a story we tell. It's a true story. It's a correct picture of what is going on. But it is, we're now learning one story you can tell for what is going on. Okay? So, and the purpose of this story, the purpose of the textbook formalism, is to make manifest two very important properties. The two important properties are the two, big principles of modern physics. We want to manifest that we have a picture of space-time processes that are local. In other words, that we don't have interactions between random points separated in space and time. So locality is one of the big principles. Lorentz invariance, the picture of special relativity, and locality is one of the big principles of modern physics. And secondly, quantum mechanics. Okay, so, and this is where Richard Feynman taught us that the way to think about quantum mechanics is by drawing all possible histories and summing over all possible histories. Again, in a classical world, there would be a single history for what happened. Classical physics is deterministic. Quantum mechanics is not. And so you have to sum over all the possible histories for what's happened. And that's why we have to sum over all the diagrams. So the sort of technical word for this is locality. And the technical word for this is unitarity. Okay, there's a matrix, this amplitude, if I go back to in to out, this amplitude for in to out is some matrix or an operator that's sandwiched between the in and out states. And unitarity is a statement. This has a consistent interpretation as quantum mechanical probabilities that says that this matrix has to satisfy that it's unitary, that S dagger S equals 1. Okay? So those are the two big principles of 20th century physics. And this textbook picture is built to make them as manifest as possible. Right? So when you have the picture of Feynman diagrams, summing over all diagrams, you then go to grad school for a semester or a year, and you learn how these principles are sort of translated into the rules that precisely take us from these pictures to the final answer. Okay? So what I want to stress is that the standard picture is completely correct. Nothing wrong with it. It's totally universal, unlike the things we're talking about now, which are not yet totally universal. Okay, so we're far from being totally universal. Okay, but the reason to be looking for an alternate picture is, first of all, just purely logically, no one said. We don't know. All we have access to is in and out, right? So it's entirely logically possible that there's a different picture for what might be going on inside, a different machine whose crank you turn to produce the answer that does not involve drawing these pictures. Okay? We have various reasons for looking for such a picture. We have various conceptual reasons internally within physics for looking for such an alternate picture, because for a whole variety of reasons we expect that the notion of space and time eventually breaks down at very, very short distances, because of questions involving putting quantum mechanics and gravity together. We even expect, for very subtle questions involving applying quantum mechanics to the entire universe, that quantum mechanics might have to be extended in some way, in very, very extreme situations. So these two giant principles of the 20th century are both under question. They're both likely to be superseded in whatever next picture of physics we end up getting. That transition is going to be at least as dramatic as whatever took us from classical physics to quantum mechanics, because we have to figure out how to get rid of space-time and how to move beyond the quantum mechanics. And it's such a radical thing that if it's true, it's very unlikely to leave all the rest of physics untouched. And so it must be, if space-time is not really there, if quantum mechanics is somehow transcended, it cannot be that, that when we think about these simple basic processes where there's no reason to question the presence of a space-time, no reason to expect quantum mechanics is breaking down, nonetheless, if they're not really there in the true theory of nature, there must be a way of talking about these things also without putting them in as sort of hardwired into the description of the physics. And this has happened to us before in physics. Precisely when we went from classical physics to quantum mechanics, we underwent such a transition. It seems as shocking as possible to lose determinism if you tell a classical physicist in the year 1850 that in 1930 determinism is gone. They'd be totally shocked. How can it be the Newtonian clockwork universe is working perfectly, everything is great, the Industrial Revolution depends on it, right? All this stuff. How can it be that determinism is lost? And the answer is in a subtle way, right? So if you told that to a physicist in 1850, they might wonder whether there's some way of talking about physics in such a way that determinism is not the star of the show. They're getting this clue from the future. And they might wonder if there's a way of thinking about physics where determinism is not the star of the show. And they're not going to guess quantum mechanics. It's crazy that they're going to guess quantum mechanics just from the clue that determinism is gone. But they can take inspiration and try to recast classical physics in such a way that determinism is not the star of the show. Of course, it turns out there is such a way of recasting classical physics. It's the principle of least action, the Lagrangian picture of physics. When you first learned it in school, it's very surprising. It looks like the particle goes from A to B, not by slavishly following F equals ma at every point, but by sort of sniffing out all the paths you can take from A to B and choosing the one that minimizes the action. That's a way of talking about physics that definitely does not look deterministic on the face of it, right? Of course, it turns out to be deterministic. It turns out to be a rewriting of Newton's laws in some cases, but it's a way of thinking about Newton's laws where the idea of determinism is not central. And of course, we now know today that this other way of thinking about classical physics, using the principle of least action, is the way that uplifts the quantum mechanics. Okay, so not Newton's laws. You don't begin with Newton's laws and do a small modification to it to get quantum mechanics. You do start from the principle of least action and do a small modification of it to Feynman's picture of summing over all the history. So this is the mysterious thing about physics, that at any given moment in time, the laws can be cast in numerous different ways, starting from seemingly radically different starting points. Some of them are better suited for the leap to the next level of description than others. And so if you have a clue for what you're going to lose in the future, it's inspiration to go back and dislodge that from your way of thinking now. Okay, so this is very abstract, very highfalutin, almost content-free seeming motivation for trying to learn how to fill this blob with something else. We don't want to have a picture of diagrams and space-time processes. We want to think that there's some other machine in here, some question mark that we're looking for that's going to give us the answer without drawing pictures of space-time trajectories. That's something that we're looking for.
So do you mean something like non-connected graphs?
Sorry?
Do you mean something like a non-connected graph?
It will have nothing to do with graphs. Okay, so I mean, it's a big question mark. Okay, so we're going to fill that with something else, but we're going to get more concrete about this as we go on. Yes, there was a question I ignored all this time. Yes, sorry.
Could you please explain a bit more locality, the thing that you said? And did you at some point mention the change between in and out?
Mm-hmm.
What do you mean by that? Can you explain this?
Yes, the change between in and out is just the following cool fact, that you can have, let's say, two processes where particles A and B go in and particles C, D, E, F go out. Okay? That's one process. That's clearly different than the process particle A, B, C goes in, particles D, E, F go out. Those are two obviously different processes. The remarkable thing is that there's one and the same function that calculates both of them. Okay? There's just a single function that depends on 6 momenta, P1, PA, B, C, D, E, F. And then depending on whether the signs of the energies, the zero components of those P's are positive or negative, you get to interpret that as a process where some things are in and some things are out.
So you don't mean reversing in and out? changing.
No, it's just changing in and out, not reversing in and out. Just declaring who's in and who's out. That's not at all obvious that those things should be related to each other. I'm saying at a super early point, this picture that all we're doing is making a matrix that's unitary is somehow already missing something very basic, because the object doesn't even have this matrix interpretation really, right? It's just something that democratically depends on lots of momenta.
Hey, what about locality?
Well, locality is a statement that you can't reach out and touch someone, right? That things can only interact when they're on top of each other. You can't pick up a phone and talk to your friend in Alpha Centauri as quickly as you like. And that's a very basic principle. It's even a basic principle before relativity, but it acquires much more significance after relativity when you believe there's finite speed of propagation for any signals. Okay, an upper bound for the speed of propagation for any signal. So fundamentally, things should only interact with each other when they're on top of each other. Okay, all right. So that's one set of reasons for looking for a different way. I mean, the zero thing is that there might be a different way. The first one is these highfalutin abstract statements about learning to do physics without the rules of space-time and quantum mechanics as being king. But the most practical thing is that when you use the standard way of thinking about things in terms of Feynman diagrams, it for sure gives you the correct answers. No doubt it gives you the correct answers. But it gives you the correct answer, but it leads you to qualitatively incorrect conclusions about what the answer should look like, right? And so that's what's been alluded to a number of times is the explosive complexity of Feynman diagram calculations. And very simple reason. First of all, the number of diagrams, depending on the kind of theory we're talking about, either grows factorially or exponentially with n. Okay, so you can just the number of terms similarly can grow factorially or exponentially. But very practically, if we talk about sort of the collision between two protons at the either at the LHC or again, just when a cosmic ray hits the upper atmosphere, this is happening gazillions of times a second everywhere around us, right? So the proton is made out of quarks. They're held together by gluons. So, for example, one process that happens here is one gluon from this proton collides with another gluon from this proton, and something happens, and let's say two gluons go out. This is something that you put on a problem set, and if the students don't do well, you don't take them as graduate students. Okay, so the next problem is if you have two gluons come in and three gluons go out. And this you would be very cruel to put on a problem set, because this already is like 30 pages of algebra. Just a horrendous mess. You would never torture someone with this calculation. You put four gluons out. That was the 220 diagrams that were referred to in one of the talks this morning. 100 pages of algebra, right? If you write big like I do, 500 pages of algebra, right? And okay, well, that's just what it looks like. You see, not every question in physics is guaranteed to have a simple answer. And as part of the chauvinism of fundamental physics is to declare interesting only those questions that have simple answers, and all the other questions to call engineering. Okay? So this looks like a classic example of engineering, right? However, also, physics has a wonderful way of punishing people who look down on engineers and rewarding morally good behavior, okay? Because some people just have to do this calculation. They just have to do it. They have to do it because experimentalists needed the answer. By the way, experimentalists need answers for up to like 8 gluons coming out today if you want to interpret data from the LHC. So this is not esoterica. These are, we really need these to compare theory and experiment. Okay, but in this famous calculation by Park and Taylor in the late 80s, I don't remember the year, was it 87? Anyway, sometime in the late 80s, people found an amazing surprise. So these gluons are particles like photons. They have a spin or a polarization. So you can have photons that are positively or negatively circularly polarized. Similarly, you can think of the gluons as being positively or negatively circularly polarized. And the shocking result is that, as it turns out, for any number of particles, if you have the amplitude for gluons 1 through n, and let's say they're all positively polarized or all negatively polarized, the amplitude is 0. Not at all obvious. Those hundreds of pages are adding up to 0, right? Or if one of them is positive and the rest are negative. It's also 0. And the amazing thing is if 2 of them are negative, then it has this famous, can you see down here or should I? Maybe I'll use it. I'll do here. Okay. There was this famous result that by Park and Taylor, oops, this sort of one-term expression. Okay, so we know that in fact in this case, and I'll be more precise about this in a bit, but if 2 of them are negative and everything else is positive, and they're negative in locations I and j, 1, 2 up to n, that this amplitude, I'll define what these symbols mean later. Those of you who know what they know them, but we'll be talking about them in a bit, is this like stunning one-line expression. Okay? So this is not supposed to be obvious. Okay? In fact, for 5 particles, nothing you can do, right? At least 2 of them have to have, they're either all the same sign, one of them is 1, the rest, or it's this. So for all those 30 pages of algebra, either give you 0 or this incredible one-term expression. And similarly, the few hundred, 500 pages of algebra for this helicity configuration collapse to a single term. And okay, now this is very, very striking. Now back then, in the late 80s, when this was discovered, this was not universally recognized as the tip of a giant iceberg. Today, we know it's a tip of a giant iceberg. And it's the iceberg that we want to be exploring in these lectures. So, but we now know, I mean, you could have already taken this as a strong hint back then, but we now know that this is happening because while the standard picture is definitely correct, once again, nothing wrong with it, it leads you to expect that these processes have 500-page long computations when the result is a single term. Right? And so it strongly suggests the existence of another picture of the world, a different picture of the world where the fact that the answer is obvious, and presumably there's no free lunch, right? So what's not going to be obvious in that picture? What's not going to be as obvious anyway is that there's something like space-time and quantum mechanics going on, right? You make space-time and quantum mechanics obvious, 500 pages, thank you, right? So if you're going to see the one-line expression, presumably the space-time and quantum mechanics is not going to be as obvious and is going to have to sort of come out from some other set of ideas, right? And ahead of time, it's clear, before you embark on trying to discover what this question mark is or this other way of thinking about things are, it should be totally obvious ahead of time that new physical ideas will be needed. That's obvious. Physical question, you're trying to reformulate physics in some way. I think it's equally clear that new mathematical ideas are needed. Why? Because the actual functions that we get in the end, no matter how you do the computation, the actual functions that we get for the amplitudes are not these like Mickey Mouse functions. They're not sines and cosines or little polynomials. They're very rich, complicated functions with all kinds of, there might be rational functions with very complicated, intricate patterns of poles. There might be transcendental functions with all sorts of remarkable properties. They're normally the output of this giant machine that's called quantum field theory, textbook quantum field theory. If they're going to be the output of some other machine that cannot be some Mickey Mouse thing, it also has to have some, interesting girth to it to be able to accomplish this. Okay, so it's clear that we're looking for things that have both new physical and new mathematical ideas. And I'll say a little bit about what those ideas are in a bit. So let me just say what our sort of program is that we'll be talking about in these lectures. So we want to find, sometimes people describe this research as, simplifying calculations for amplitudes. And that does not interest me one iota. Okay? In fact, if this question mark turns out to be more complicated, I wouldn't care that much. The fact that the answers are so shockingly simple is a clue that this other picture exists. But for me, it's definitely not an end to itself. I actually don't personally care about these amplitudes that much. What I care about is the story they're telling us about the principles of space-time and quantum mechanics. That's what I really, really care about. And so that's what we're not looking to find some tricks to make the calculation simpler. That's incredibly important for getting theoretical data, right? You know, had these people not done this unbelievably heroic work to get to that one-line answer, we would not have gone down this line of work. So there's absolutely nothing wrong with tricks. It's just not what I'm personally interested in. It's not tricks. It's not starting with the expression and manipulating it, changing variables until you get something a little simpler at the end. The goal is to sort of turn everything on its head and find a different question to which the amplitudes are the answer. That's what we want to do, okay? So we want to find, so that's been the mantra for a long time, you know, what is a new question to which the amplitudes are the answer? Okay, that's what we're interested in. So again, we want to fill in this question mark here, right? There's some other thing which is going on to produce crappy question mark, okay? To produce the amplitudes. And okay, now, where is this question going to live? Right? This question is going to live, you see, the conventional things to fill in the interior here with space-time trajectories, right? So definitely we should not have any picture of space-time trajectories. On the other hand, the amplitudes depend on things. They depend on the momenta of the particles. Those momenta are things that you see at infinity. Okay? So the amplitudes depend on something you can call the sort of kinematic space. Okay, so this question that we're looking for should live in the kinematic space that specifies the amplitude. Okay? So we're looking for a question in the kinematical space that specifies the scattering process. Whose answer is equal to the amplitude, whose answer is A. Okay? What is this kinematic space? Again, the amplitudes, sometimes we're calling A, sometimes we're calling M, sorry. For example, in the simplest way, they really depend on n momenta. Okay? So these are these on-shell momenta that we just talked about. So pi in the Lorentzian variant, we'd say pi squared equals m squared, on-shell momenta. So this is my kinematic space, the space of n momenta, and 4 vectors. Okay? So that's the first thought about what this kinematic space is. Okay? So we descend from these lofty heights with a thud that we somehow have to find a question in the space of P1, P2, P3 up to Pn. Okay? We have to find an interesting mathematical question in that space whose answer is the amplitude. Right? We refuse to talk about, so if one of the physical ideas here, let me put it here. See, when you draw a Feynman diagram like this, even the sort of simplest example of a Feynman diagram, here you'd have the particles 1 and 2 and 3 and 4. And here we'd have this intermediate particle whose momentum is given by P1 plus P2. Okay, and so it's plain that if P1 squared, let's say, is equal to 0, the particles are massive. If P1 squared, P2 squared equal to 0, this does not mean that P intermediate squared is equal to 0. It is not equal to 0 in general. Okay? That's why we call these things in textbooks virtual particles. They're not real because they're not on shell. They're also not real because they don't go click, click, click in an experimentalist detector. They don't travel over infinite distances, okay, which real particles do. Feynman diagrams are littered with these virtual particles. And that's, again, they're there in order to make locality and quantum mechanics manifest. They're also directly responsible for the explosion in complexity. Okay, so the physical idea is to banish virtual particles. We never want to talk about virtual particles. We somehow want to do physics where we never talk about the notion of a virtual particle. Okay, that's a physical, one of the physical ideas. And so that means that the space, the kinematic space in this case is just the space of n momenta. Right? Now, in fact, we're going to do a little more. Let me just mention a couple of natural choices of the kinematic space.
But so if you think about momenta, do you think like about space-time in the background, or like, I mean?
No, these are just things that specify what's being observed at infinity. Okay, so these four momenta are really labeled by three things, right? Because they're on shell. So that's right. Now there's some space here. It's not space-time. It's not the conventional space. This is just a space of n4 vectors, okay, that are each on shell. In this space, there's no notion of time. There's no notion of two things being close together. There's no notion of a metric. This is as arid and boring a space as it seems like you might have, okay? Yes?
Sorry, could you please elaborate why the right question for you is to ask what question the amplitude is an answer of?
Well, it's a question that I try to motivate. But if you like, it's trying to be as closely tied into the actual observable as possible. This kind of philosophy has had a sometimes glorious, sometimes tragic history in physics, okay? Where you take the attitude to stick to the observables as much as you possibly can. Sometimes it's been an excellent idea, sometimes it's led people astray. I'm making a bet this time it's going to not lead us astray, and it's a good idea, okay? But we want to hold on as much as possible to the direct observables. The virtual particles you do not see. All those momenta inside the diagrams you do not see. What you do see are the asymptotic momenta, so that's the space we're going to live in. That's the space in which we're going to ask our questions. So there's actually a few versions of the kinematic space. This is going to be loose. We're going to make it more precise, as you'll see. But this is kind of our canvas, right? Our canvas could be one. It could be the space of four momenta thought of individually, okay? So this is really like a space of, four vectors. It's like a 4 by n matrix. Okay, so my kinematic space is a space of 4 by n matrices. We're going to have to ask a question of the space of 4 by n matrices and get an amplitude out as an answer. Okay. Another possibility, so this is kinematic space 1. Another sort of qualitatively different possibility, closely related but not the same, is to take advantage of the fact that we know the theory is Lorentz invariant. So the amplitudes should not, I'm still being a little bit loose here, they should not depend on the individual momenta, they should depend on dot products of momenta. The answer only depends on dot products of momenta. So here the kinematic space will be made out of dot products of momenta. Okay. So it's very similar, but in this case the kinematic space is like, 4 by n matrix, d by n matrix. In this case, it's like a roughly n squared. And is that we've been finding in these kinematic space a question to which the amplitude is the answer. And they've really roughly come in two waves. The first wave was something very close to this. And this is a story of the amplituhedron. Okay, so we're going to talk about this. A second wave starting in 2017. So this is going back to starting in sort of 2009 up to 2013 or so. A second wave started in 2017, thinking about this as the essential kinematic space. And this, first of all, connected to the associahedron. And we'll say more what this is about. But which developed into a more general story of amplitudes associated with curves on surfaces. Or sometimes what we're calling surfaceology. Okay? In both of these cases, there's a sort of a uniform picture for what the character of the question is. And I want to, even though the nature of the questions end up being quite different in the two cases, okay? But the sort of character is basically the same. And this is going to be a cartoon, okay? But here we have our kinematic space. Okay? And in the kinematic space, there's going to be a natural region, P, that you can call the positive region. Okay? So there's going to be some notion of positivity is going to make a crucial appearance in this story. So there's going to be a positive region in this kinematic space. And the scattering amplitudes, are going to also be associated with certain differential forms that live in this kinematic space. They're not even going to be top forms in general. They're going to be some lower dimensional forms that live in this kinematical space. They're going to be some little d-dimensional forms. We'll say what little d is later. But in this big kinematical space, there's also going to be some natural little d-dimensional subspace. Okay, so there's some little d-dimensional subspace. The intersection of this subspace with this positive region P is going to be a shape. Okay? That shape is going to be a positive geometry. And this form, you see, this form just lives in the kinematic space. It is a form, right? Lives everywhere, but it's finally entirely determined by the requirement that when you take this form that lives everywhere and you pull back to this subspace, let me call it S, SD. When I take this omega that lives everywhere and I pull back onto this subspace SD, this is the canonical form for this, you can call it the sort of generalized amplituhedron, which is the intersection of this positive region with that plane. All right? Right? That's the sort of general story which has emerged. Now, the story of the amplituhedron from the 2013 paper did not yet look like this. In fact, if we did not hear about the B amplituhedron earlier today, we would not have seen it. Okay, so there's been some developments to bring things to the form where we can talk about it in this language directly formulated in the kinematic space. Okay, and that's what I want to tell you a little bit about is sort of conceptually what is going on and how that works. But this story ends up being exactly the same for the two pictures. Just the nature of the positive region and the nature of the subspaces depends on whether it's the amplituhedron or the other story involving surfaceology, but it's always the same. Amplitudes are canonical forms of positive geometries. Where those positive geometries live, they live in kinematic space. What determines them? Some interesting intersection of a positive region with some appropriately chosen subspaces. Okay? Okay? All right. So with that, yes, there was a question. Yes.
Can you repeat the motivation why you expect the amplitude only to depend on the inner products and the dot products of these?
Oh yes, that's just. I mean, this is again somewhat loose. If you have the particles with spin, there's other things as well. You can talk about polarization vectors, but in general, all the data are various vectors or tensors or even spinors that are that transform into the Lorentz group. But since the amplitudes are Lorentz invariant, they only depend on Lorentz invariant combinations. Okay, so if you only have momenta, then they only depend on these dot products. The main thing that I want to emphasize is the difference between things that depend on the particles individually versus that depend on pairs of particles. Okay, and you'll see when we do particles individually, we'll be in the world of Grassmannians, amplituhedra, blah, blah, blah. And here we'll be in the world of surfaces, curves on surfaces. Why curves on surfaces? Because an open curve on a surface has a beginning point and an end point. Okay, and that two-ness of where it starts and ends is reflected in the two-ness of the fact that our kinematic space depends on dot products here. All right? Now, so with this very rough guide, let me just say what my plan is for the lecture. So today what I'd like to do is talk about the amplituhedron, talk about this story. And we had a very, very nice lecture this morning on the combinatorics of the amplituhedron. I thought maybe for this audience, I would explain a little bit where the amplituhedron came from. Okay, where it came from, why it's not such a crazy seeming thing, and you know what the motivations were, just so you see sort of step by step how it emerged. And also how it finally leads to this picture, because if you're familiar with the amplituhedron, the y equals c dot z picture looks absolutely nothing like this. Okay, so it's a number of steps to get to that picture between 2013 and 2017 that's associated with the picture that we heard about this morning that defines the amplituhedron in terms of these twistor variables which anyway, have a very natural interpretation in terms of this kinematic space. Strangely enough, only after that picture for the amplituhedron was developed in 2017 did it become possible to see this in hindsight much, much simpler picture for these simple scalar theories that, however, was missing the sort of key idea of looking for this pattern, okay, of a positive region in a bigger kinematic space and a subspace on which the amplitudes reveal themselves. Okay, so this really is a kind of a common motif in this entire story so far. So today I want to tell you a little bit about the motivation behind the amplituhedron. Tomorrow I'll tell you about surfaceology. We'll start again. We'll think about the kinematic space again, and we'll see the story of surfaceology. And for my third lecture, I want to talk about something else, which the recent developments with over here have made possible. Something I'm extremely excited about is all of these pictures, even these new geometric pictures for amplitudes, they have this feature I'll stress in a moment. There's something basically recursive about them. Okay, so you build these geometries. We heard a definition of positive geometry earlier. But the definition of positive geometry has some recursive quality to it. You go to a boundary, you see something that looks like a positive geometry again. And this recursive feature is kind of there in all of these pictures that have to do with amplitudes. That one way or the other, think about amplitudes as very simple when there's few particles, and you put them together, glue them together to make more and more complicated ones. We can think about it in this super direct way with Feynman diagrams. We can think about it in this much fancier way, which exposes, wonderful, exposes all these things, positive geometries, blah, blah, blah. But still, if you want to know what is the million particle amplitude, you're not going to get the million particle amplitude without first getting the million minus one particle amplitude, million minus two particle amplitude, and so on, right? It still fundamentally has a feature that you have to build something complicated out of simple pieces. And I've long sort of fantasized that something really new about amplitude should let you go the other way, sort of give you the amplitude for infinitely many particles first, kind of a second theory, just a formulation for what the physics is and limit where the number of particles is infinity, and then give you a systematic 1 over n, where n is the number of particles, expansion to sort of correct and bring back to a finite number of particles. And that's, I think, what we're now seeing, and I want to tell you about in the third lecture. It's really sort of a qualitatively different picture for what the amplitudes are that gives you access to a regime that we did not know how to access before in physics, where the number of particles is like literally infinite, okay? And then you sort of back away from that, from a systematic expansion. So that's the rough plan. But again, I'm in no rush. We don't have to get through everything, so we can stop for as long as, or as little as you want on any of these subjects. All right. Let's just stop there. I've barely said anything, but in the little bit that I've said, are there any questions? I'd be surprised if there were.
Sorry, can you say something about measuring, or is it like negative and positive infinity?
Yes.
Like, what's the meaning of that?
Yeah, well, I mean, it's an idealization. But let me just say, practically speaking, when experimentalists collide particles at the LHC, experimentalists are about your size. Maybe their brains are a little smaller. But I'm kidding, recording. I'm joking. They're my favorite people in the world. I love you, experimentalists. They're big. They're meter-scale creatures. They're scattering protons that are 10 to the minus 14 centimeters big. Okay, so the experimentalists are huge compared to the things that are being collided. And also, the LHC is 27 kilometers around. 27 kilometers is nearly infinity compared to 10 to the minus 14 centimeters, the size of the proton. But more conceptually, whenever you do any kind of observation, you want to disentangle the physics of the apparatus from the physics that you care about. So that's why you put them far away, right? So the apparatus is far away. You don't put the apparatus right on top where all the collision is happening, because then the apparatus is interfering with what you're trying to measure. Because it's just a very important part of the active observation in quantum mechanics is to really decouple the system from the apparatus from the system as much as possible. So the experiments start and end at infinity. Okay. Did that answer your question?
Yes.
Okay. Any other questions? Yes.
What is the number number d?
Oh, it's a number. It depends on the process. Depends on n. But if you specify your scattering process, this d is going to depend on that n in some way. Okay, so it depends on the context. Okay, but there are some. But for any particular process, there is some particular dimension subspace and a way of choosing that subspace so that this is the answer. All right.
And is this subspace the boundary of the
No.
the intersection with the
No. I mean, this subspace intersects with the positive region. It intersects somewhere, and this somewhere has a has a region that it's an interior and has boundaries of all codimension, and the intersection of S with this positive region P is a positive geometry. That's the idea. So you then want to find a canonical form for that positive geometry. Okay. Now the cool thing is, you see. If I just told you loosely, amplitudes are canonical forms of positive geometries, great. But then you think a little bit and say, well, what could that mean? I mean, the amplitudes depend on a bunch of momenta. But a positive geometry is like this square, right? Or this pentagon, or this fancy shape with this particular parameter. What could it mean that the amplitude, which depends on all possible momenta, is the form of like a positive geometry? And this picture solves that. You see, it tells you that the amplitude is a form. The form lives everywhere. It lives just defined on the full space. But when you pull back on this particular subspace, it has a magical property that when you pull it back to that subspace, it becomes the canonical form of the positive geometry you see on that subspace. If you move the subspace around, well, in detail, the shape of the positive geometry will change, the form will change, but the underlying form that lives in the whole space is uniform, is always the same, and is literally interpreted as the amplitude. There's a little bit of an extra step to go from a form to a function. Okay, I have not told you that, so that's a little extra thing, how we convert these forms to functions. And the nature of this pullback is going to tell you precisely how to do that in all cases. Okay, it has a slightly different answer in the amplituhedron case and in this case, but always, in the end of the day, the amplitude is really that object. Okay. All right. Okay, now, maybe before getting into more details, I want to say one more thing about what. So, let me say two more things, and then we'll start into something more meaningful. Maybe as I'm erasing, I can say that we're going to spend some time kind of like slightly moving around in what we mean by this kinematic space. It can be the space of momenta to begin with. We'll muck around with it a little. We'll talk about spinor helicity variables. We'll talk about momentum twistors, momentum twisters. But they're all just different ways of labeling the n momenta for the particles. Okay? So, and similarly, that pi.pj space. The pi.pj space, naively, it's a space of n squared numbers, pi.pj. Of course, momentum conservation, which says that the sum of the p's adds up to 0, is going to put a few relations on those guys. So it's not quite an n squared dimensional space or an n choose 2 dimensional space. It's a little lower than that. And there's various ways of coming up with nice bases for that space. But what I want to emphasize, we're really talking about those two spaces, one way or the other, up to simple basis changes. So it should really surprise you that there's anything you can do in these seemingly stupid spaces that is going to produce all the richness and complexity of amplitudes. Okay? And just to say now, a big word that is important here, that brings almost everything to life. There are two words that bring everything to life. The notion of an ordering, that these n momenta are not handed randomly to you, but are naturally ordered in some way. P1 followed by P2 followed by P3, and the existence of a cyclic ordering. Okay? This is related to the fact that all the physics that we're talking about here has to do with the scattering amplitudes for particles with color. We'll say that a little more precisely in a second, but I just want you to get this in your mathematical heads right away, that somehow without the notion of a cyclic ordering, there's nothing to do. With the notion of a cyclic ordering, poof, all of a sudden, a lot of things become possible. And then also the word positivity. Okay? And again, as we heard in the review about positivity and positoroids and Grossmanians, this is very much reflects something that if you're just looking at general matroid stratification, impossibly complicated, any algebraic variety can be realized in that world. You say the word cyclic ordering, you don't care about the matroids are about arbitrary linear dependence between vectors in arbitrary orderings. But you say you only want to keep track of the linear dependence between consecutive sets of vectors. You give a cyclic ordering, you say the word consecutive sets of vectors, then all of a sudden now there's a structure. Now there's a very rigid structure, and this positoroid stratification, which also goes along with the notion of positivity. So somehow this very, very basic thing, which was seen in the story of going from random matroids to positoroids, has to do with ordering and cyclicity, and has to do with the presence of color when we talk about physics. That's kind of responsible for what can breathe some life into these seemingly very arid, almost either empty or too complicated mathematical spaces. Okay, so just keep that in mind. Now, something else that I want to say is, virtual particles in the standard way of doing field theory has a purpose in life. Of course, we said that it's supposed to make space-time and quantum mechanics manifest, but it actually does more than that. It does that in a way that's very sharply reflected in what the actual formulas look like, what the actual amplitudes look like. So let's say, again, we have this sort of simplest process. Maybe there's a coupling constant g here at this vertex. G is nothing very complicated, they're just scalar particles. So the amplitude for this process following standard Feynman rules would be g squared over p1 plus p2 squared minus m squared. Okay, so that's this momentum here, this intermediate momentum as p1 plus p2. Okay, so that's what this very, very simplest amplitude looks like. And there might be another diagram, which is this one. So this would be g squared over p2 plus p3 squared minus m squared. Okay. Now, this example is extremely simple. You can compute the Feynman rules, no problem. But let's say you were super lazy. You didn't even do this. Okay? And someone came to you and said, I did the calculation. Here's the answer. Can you check that they're right or wrong? Right? There's a very easy way we can check whether you're right or wrong. In other words, the way in which locality and unitarity are reflected they're reflected in very precise, sharp properties of the amplitudes. And it's in the following very simple way. Locality, this is true, I should say, this is true for these simplest tree amplitudes. I'll say a little bit about what's known at loop level in a bit. Locality is reflected in the fact that you only have simple poles. So in other words, only things that look like some 1 over p squared minus m squared. You don't have things that look like 1 over p squared minus m squared squared. Don't have that. You definitely don't have things that look like 1 over p squared q squared minus r squared t squared. You don't have that. Okay? The only things you have are simple poles, and these p's that show up can at most be sums of subsets of the momenta of the external particles. Okay? So that's a statement of locality. That's a statement in momentum space that the particles met at a point. And so the momentum of this thing that they're making is the sum of the momenta incoming to them. Okay? None of these other things are allowed. Right? So if someone said, I did the calculation, and they produced something that had this kind of term in it, they're lying to you, right? Okay, so locality is where the poles are. The poles are simple poles, and they're located only in this spot where the p's are sums of subsets of the momenta. Unitarity is the statement that, so this is space-time locality. This is quantum mechanical unitarity. It is a statement that in the neighborhood of the pole, you have to be able to interpret. You see, this is like a resonance, right? So when this is going to 0, literally the amplitude is blowing up. So it's like the swing amplitude is blowing up when you go on resonance, okay? So the amplitude is blowing up. There's a pole. So as p squared goes to m squared, the amplitude indeed goes like 1/p² minus m squared times something times some residue. But this residue has to be interpreted as the product of the in amplitudes going in and making this intermediate state, and then the intermediate state goes out and makes the out guys. Why? Because you're getting a pole precisely because the virtual particle is becoming real in the standard language, right? This is now becoming real. On the pole, this part is really interpreted as that amplitude now, right? It's not some unphysical virtual particle anymore. This is a real particle. And so you have to be able to interpret the amplitude as this sequential process where you first made the intermediate state, then it propagated out a long distance, and then it decayed, right? This propagating a long distance in position space is reflected by the presence of that pole in momentum space, okay?
Sorry, can you say this one more time, like how if you make this cut, somehow it amounts to taking this residue?
Yeah, you see, I mean, the point is that you see it, first of all, in the concrete computation, right? As p1 plus p2 squared goes to m squared, this is blowing up. What's the residue of it's blowing up? It's g times g. Well, g is the amplitude for just this part, and this g is the amplitude for the other part, right? And this happens in total generality. Whatever blob is happening here and whatever's going on there, once that momentum goes on shell, as far as this part of the graph is concerned, this is as if you're calculating the amplitude for that guy. And this is as if you're calculating the amplitude for this guy on the other side, right? So that's why it's just obvious that's the point of the standard formalism, to make it obvious that on these poles the amplitude factorizes into the product of a left and a right piece, okay?
Could you explain again how locality is related to simple poles?
Yeah. Locality is related to simple poles because this is really a sort of translation from what's going on in momentum space, where we're thinking about these amplitudes, to position space, where the notion of locality is sort of manifest, right? So in position space, all the things that either things are totally local in position space, or it can have things like inverse square law forces, say, right? Now, why can we have things like inverse square law forces? Because they actually satisfy local equations of motion. Things like Laplacian potential equals 0, right? So because you have local things like that, the only way you can get any momentum downstairs is by inverses of things like Laplacians, which look like 1/p², okay? So the reason there's no 1/p⁴ is that we don't have like Laplacian squareds in our description of the physics, and that has very good reasons that are also related in some way to a unitarity. But essentially, if you imagine any conventional picture of a Lagrangian upstairs as two derivatives, ordinary equations of motion, and so on classically, then when you compute anything with them quantum mechanically, you'll never get anything other than poles that are at positions of 1/p², and those 1/p² just come from inverting the two time derivatives, if you like, in the underlying Lagrangians in position space. Did I answer your question?
Yes, thanks.
Okay. Okay, so all right, so now. So this is very beautiful because it means that if we're looking for some sort of whiz-bang new question in kinematic space to which the amplitudes are the answer, they have a job to do. This question has to produce functions. The functions have to have poles in special places, and only these places, not other places. And they have to have a reason why on the poles they factorize into the product of lower objects of the same sort. Okay. So now. What we've been hearing about earlier today in the story of positive geometries and canonical forms are an example of what that could look like. You see, one way of guaranteeing that you have objects that have poles in the correct place and that factorize is Feynman diagrams. That's where they came from, right? That's exactly what that makes it as obvious as possible. Okay? But we're trying to see, is there another kind of object that can give us the same kind of structure? Okay? And so, if we think about roughly we have positive geometries. And their canonical forms, just I'm not going to repeat Aliyah's beautiful lecture, but let me just say a little bit about it. See, on this side, there are some real geometries, right? There are some real geometries. Maybe they could even have curvy boundaries, okay? But again, the idea is that they have boundaries, at least loosely. We had a more precise definition before, but they're boundaries of all codimension. Okay? The word positive is there because kind of in the simplest cases, like the inside of a triangle, how do we talk about the notion of an interior is intimately related with notions of positivity, right? If you want to talk about the interior points of a triangle, one way to do it is to take a positive weighted average of the vertices to give the convex hull of the point. So that's where the word positive comes from, right? Another way is to specify a bunch of inequalities that you have to be on the positive sign of all these lines, okay? Both cases, the notion of interior has to do with a notion of positivity, right? All right, so on the one hand, we have these, we have real geometries with the property of having boundaries of all codimension. On the other hand, we have these canonical forms associated with them, which have this feature of putting d log singularities. So dx, so locally, they look like some dx. If it's an n-dimensional space locally, they will look like this near the boundaries. And with logarithmic singularities on and only on the boundaries of P. Okay? And already if we talk about the simplest cases, I'm just going to recap some of the things that, quickly, some of the things Aliyah said. But just to get an appreciation how even very, very simple geometries can already give us rather rich functions. If we talk about the very simplest case, let's just do this. Which Aliyah also talked about. Let's talk about the sort of very simplest case of an interval, right? We talk about an interval, so let's say this direction is x, here's x equals a, x equals b. What is the canonical form for this guy? Well, it has to have logarithmic singularities at x equals a and x equals b, so what can it be? It's a dx over x minus a, clearly, and dx over x minus b. But there's something important here. Is it a plus sign or a minus sign? It's a minus sign, so these are actually oriented. It's a minus sign because if it was a plus sign, this would also have a residue at infinity, right? So this shows very simply already that it's important that you only have residues on the boundaries and only on the boundaries, nowhere else, okay? And that dictates the relative sign, okay? Let's do the next example. The triangle, right? So let's say I have a triangle, so this is x and y. So here's y equals 0, x equals 0, 1 minus x minus y equals 0. Now what is the canonical form for this guy? Well, it's a two form, so it's going to be dx dy. Clearly, it should have a singularity on x equals 0, y equals 0 here, so it's clear that we should have these factors downstairs. But now you see what's cool about this. Again, Aliyah talked about this in even more interesting examples, so let's just quickly do it again. So this clearly has singularities, the correct codimension 1 singularities, but you need more. The idea that it has singularities on and only on means that if you take any residues, you should keep seeing the canonical forms for the lower dimensional boundaries. So let's say I take the residue here at x equals 0. So taking the residue at x equals 0, just in this case, just means erasing dx over x and putting x equals 0 there. So if I take the residue of this form on x equals 0, it's going to be dy over y, 1 minus y. So you see, that's very beautifully. Here I'm at x equals 0, and this form is exactly this form for this interval. Again, it's y, 1 minus y. Note there's no residue at infinity. It goes like dy over y squared at infinity. Great? So it only has residues on and only on the boundaries of the triangle. Again, you can check the other ones. But already we can have some fun with this example. Even if we do something as dumb as a square, or I'll draw it like this. Every attempt of my life, I draw them with parallel sides. I've never not drawn them with parallel sides. Okay, so all right, so let's say this is a square, and there are some. I'm not going to write them explicitly, but there's some lines: line 1, line 2, line 3, line 4. Each one of these things is like an a1x plus b1y plus c1, right? So this line is where that equals 0, and so on. Okay. So what is the form for this guy? Well, again, it would be dx dy. Now, clearly, it has the 4 lines downstairs, L1, L2, L3, L4. But now you see that this cannot be the answer, okay? Because this guy has singularities all right when any one of the L's goes to 0. But let's say I take the residue where L1 goes to 0. Then it will also have a singularity when either L2, L3, or L4 goes to 0. Okay, and some of them are good and some of them are bad. So this is L1. And so you see, there are these 2 bad points. So this is where L1 and L4 meet. That's good. That's that point. When L1 and L2 meet, good. That's this point. But we also have where L1 and L3 meet, which is here. This is L1 intersect L3. That's not on the square. Okay? So similarly, we have where L2 and L4 meet, which is also not on the square. Right? And so that cannot be the right form. We have to have something that puts a vanishing residue here, but then that tells us precisely what it has to be. There's this unique line, L, which is the line that precisely passes through this point and that point. It puts a 0 there, and so that gives us the form. We see already something as simple as this has a kind of rich, interesting form. It's not just some trivial thing with the product of all the factors downstairs. If you want to do the pentagon, then you have this thing, right? Now you have this is my pentagon, but I have these sort of 5 bad points outside. And so now the form is, again, we'd have dx dy with the product of the 5 lines downstairs. But now I have to have something that puts a 0 on all of those 5 points, and there's a unique conic that passes through 5 points. Okay, and that's the conic that you put upstairs in order to get the canonical form. That already shows you how interesting this object is, right? Already for a pentagon, it knows about these conics that pass through all these points, and you put almost nothing in other than that you just have a pentagon, and you start getting some rich and interesting objects out. Okay. Okay, so that's just some feeling, and so one thing that you see here is that the boundary structure of positive geometries is therefore reflecting the pole structure of the canonical form. Okay? So the basic mantra is going to be that amplitudes are canonical forms. Okay? And so poles of the amplitude, are, again, of course, poles of canonical forms. But this is then related to boundaries of P. So the amplitude is the canonical form for some positive geometry P. The poles of the amplitude are poles of the canonical form, and these are related to boundaries of P. And so, roughly what we're looking for, we're looking for some geometries. If we want to find some alternate origin, some alternate understanding for where locality and unitarity come from, right? Remember, we've now translated those principles into very sharp properties of the amplitude. The amplitude has poles in particular spots. On those spots, it has to factorize into lower amplitudes, right? If we're now thinking about amplitudes as canonical forms of some geometries, then this translates into a statement that's naturally a question that lives within the world of these geometries now, without making any reference to Feynman diagrams and particles and all the rest of it. They have to have poles in the right spots means they have to have a particular kind of facet that we have to, or boundaries that we're going to sort of discover precisely what that should mean, okay? And they should factorize on the poles means what? It means that on those facets, the geometries should look like either precisely or a little loosely, we'll see the precise meaning of it, products of lower positive geometries in that same world. Right? So that's the kind of thing that we are looking for. We're looking for that kind of set of mathematical objects, those sorts of geometries that have the property that when you go to their boundaries, they factorize into products of other things that look like themselves. Right? That's the kind of structure that we are after. Okay, so if anyway, I can say it. Just going to write it again.
So Nima, that is not immediately obvious from the Feynman diagrams, right?
Sorry.
There's factorization probably.
It is. Exactly. That's what I was saying. The location of the poles and factorization is as obvious as possible in Feynman diagrams. When I say that as obvious as possible, for scalar theories, it's 100% obvious. Okay? There's really nothing more to say than what I said. And it's simply that when you go, I mean, in Feynman diagrams, it's clear that the only poles are propagators, because that's what they are. And then it's clear when you go in the neighborhood of a pole, then, as far as the left part of the diagram goes, it just thinks that p squared is equal to m squared. So that part of the computation is just what you compute if you're calculating an amplitude. Similarly for the right part, it's exactly what you compute if you're computing an amplitude. It's just taking the product of the two amplitudes. Okay? Right? Now, it's maybe slightly less obvious when you have particles with spin, because now when you're exchanging them, you're sort of contracting their, they have maybe some vector indices. And so those vector indices kind of like sniff from one side to the other. But anyway, it's a two-line argument to essentially see that you still get factorization. Although to get factorization, you need to have all the machinery of gauge invariance. Okay, so if you're just you've never heard of gauge invariance, you don't care, you're trying to build rules for gluing things together, you're just having fun playing with diagrams. In order to ask to have factorization, factorization will force you to build a gauge theory, even if you didn't want to. Okay, so that's a sense in which the sort of Yang-Mills structure and so on is completely forced on you by these requirements of locality and factorization. Right? So that's and there's no choices. Once you start thinking in this way, it's not like the world could have been 10,000 other ways and it chose to be this beautiful way described by Yang-Mills theories. There's simply no other way it could be. Right? So that's really uniquely forced on you by these requirements.
Sorry?
Yes?
When you talk about the unitary principle and the combination of amplitudes, you basically want to combine amplitudes in the way that the probabilities sum up to 1, or what is it exactly?
The statement of the probabilities sum up to 1 is almost tautological, okay? Because no matter what probabilities are, you could always normalize them by the sum of all of them, so they add up to 1. What's not tautological is that the probabilities are associated with matrix elements of a unitary operator. That it's linear. So there's a linear unitary operator that gives you the amplitudes that you square to get the probabilities. Okay? So the fact that it's a linear unitary operator translates into these statements. I gave you the sort of intuition for it, which is that you're making the intermediate particle. But it really strictly follows from taking the statement S dagger S equals 1, taking matrix elements of the statement S dagger S equals 1 between initial and final states leads you to the same conclusions. Maybe I'll say, as I'm erasing the board, that all of these things I've been talking about have been for tree amplitudes. Now, in general, there's also loop diagrams. So, we can have diagrams that look like this. And we can also have diagrams that look like this, right? And of course, what's special here is that here, because they're trees, all the momenta are determined by the external one. So that momentum is p1 plus p2. But here it's not true. If I give you 1, 2, 3, 4, this momentum is not determined. I just have to give it a name. I could call it L. And then that one would be L plus p2, and this one would be L plus p2 plus p3. And this would be L minus p4, let's say. But the momentum itself is not determined. And so there are some rules for this picture, but in the end, we're supposed to integrate. If we're in d space-time dimensions, we're supposed to integrate ddl in this very simple case, something like 1 over L squared, L plus p1 squared, L plus P1 plus P2 squared. If the particles are massless, L minus P4 squared. Okay, so we have to do some integral like that. Okay, so the final function only depends, the final amplitude only depends on the momenta. Again, everything only depends on the momenta, right? Of course, infamously, these are complicated functions, right? If I do this here, I put masses here, I'm in 4 dimensions, everything is massless. These are already interesting dilogarithms. Okay? So they can be very complicated functions. So the actual amplitudes in the end of the day depend on the momenta. Now you can ask, I told you that if someone told you they calculated the tree amplitudes, and they handed them to you, you could check if they're right or wrong. You could check if they're right or wrong by seeing that poles in the correct spot and they factorized all the poles, right? Now let's say someone claimed to do the one loop calculation. They handed it to you. Now it has a bunch of dilogs, logs, more complicated things. Can we check if they're right or wrong? Okay? And being consistent with these principles of locality and unitarity, we don't yet know, in the year 2025, what the rules are, if you give me the final function. We happen to know what they are at one loop. Okay? At 2 loops, maybe Johannes knows 85% of the rules. Okay? Maybe Ruth knows, well, I won't distinguish between the two of you, an equal large percentage of the rules, but not 100%. Okay? That's the frontier in the year 2025. It's a really massive embarrassment, if you ask me. That no shade on you guys. It's a hard problem. But what is the problem? The problem is that we do not know that the unitarity is easy to check. Basically, S stagger S equals 1 is not hard to check. The hard part is locality. Really, it's really causality is the real nub of the matter. You want to see that the function that you get is somehow, which is only, remember, an in-out measurement. You want to see that it's compatible with some kind of picture of local evolution in the interior, but you want to see what the fingerprint of that is on the final answer. And since the 1800s, we've known that things that are local in time and space, when you Fourier transform to go to energies and momenta, have nice analytic properties in those variables. Okay, so if you've taken an electrodynamics course, you'll prove somewhere that the index of refraction in materials is always bigger than 1. And the argument uses something called the dispersion relation that takes advantage of some analytic properties by very simple fact that Green's functions vanish for, causal Green's functions vanish for t less than 0. They're only non-zero for t bigger than 0. It implies some analytic properties for these guys. So we've known for a long time it's somehow analyticity properties of these functions that are reflecting causality. And the analyticity is very easy to talk about at tree level because they're simply rational functions. So all you have to do is characterize their poles and their residues, and we did that. Okay? But beginning at loop level, they're complicated functions. They have branch cuts, and it's much more tricky to sort of control and get an understanding of what their analytic structure should be, even sort of to predict ab initio what to expect they should be. We happen to know the answer at one loop, in a sense by exhaustion, because we know what every possible function is that can show up at one loop. And so that gives us a sort of big enough basis in which we can check. If you give me an answer, I can check if I can expand it in that basis of legal functions and see if it's right or wrong. All right? But at 2 loops, we don't have that basis of functions. Never mind at the higher loops. Okay? So as far as the final answer goes, in the year 2025, we do not know how to check. If someone hands me a 3-loop answer, is it right or wrong? I don't know. I can check that it shows that it's wrong, right? We can check some things that we know have to be satisfied. We have lots of checks, but we don't think we have all of them. So we don't know the sort of exhaustive check. Maybe history buffs in the audience, if there are any physics history buffs, will know there was something called the S-matrix program in the 1960s. The S-matrix program in the 1960s was superficially about something that sounded similar to what I'm talking about here. They wanted to find some way to calculate scattering amplitudes without talking about Lagrangians and Feynman rules and somehow directly imposing physical consistency conditions. But their philosophy was essentially 100% backwards for what we're talking about now. Because they somehow believed that they could derive from the top down what these consistency conditions were, what these analyticity properties were to reflect causality and unitarity. And they tried for 10 years and they failed miserably. They had one great success where they retreated to things at tree level, where we can understand things just having poles, and that momentary retreat led to the discovery of string theory. So that was wonderful. Glad that they made that momentary retreat to that special case. But the general case, they had no idea what the solution was back then. We still don't have any idea what the full solution is now, even though we know much, much more than they did then. What we're trying to do with this program of positive geometries is exactly backwards. We don't want to slavishly, put on our responsible person hats and derive what the constraints are from evolution and causality. We just want to guess the answer. We just want to find the structure that's the whole damn answer, and then read out what those properties are from the object, rather than try to do this ultra-responsible thing of deriving them from the top down. Okay, so it's not as systematic. It's much more adventurous, but it's at least not doomed to fail, or at least we're not making the same mistakes as the past. At least we're trying exactly the opposite thing that they tried before. We might fail, but it'll be for different reasons and hopefully more interesting. All right, bottom line, we don't know. So the honest kinematic space. Functions of momenta, already we don't know how to check at 2 loops. We don't know how to check whether answers are right or wrong. Okay? There is something we can do, though, that's a little bit cheating, but we've been doing this business for a while, okay? Which is that we're going to retreat, not to the full amplitude, but, in this business, other people are doing other things, right? But in this business, we retreat to just talk about this guy, right? So this is something that you can call the loop integrand before you do the loop integrals, right? All right? Now, the loop integrand now depends both on the momentum of the external particles as well as on a bunch of loop variables, right? So that's our extended kinematic space now. Our extended kinematic space is going to have momenta and some loop variables in it. Okay? Now, why do we do this? Because this loop integrand is, again, a rational function. Okay? And the pole structure of this guy is completely determined, much like it was at tree level. Okay, so here's the extended statement. Okay, so at tree level we know that if I have an amplitude, I'm going to use this symbol here. This is deliberately an ambiguous symbol. It can look like derivative or boundary or pole. It means all of those things, okay? But this is a cartoon. But let's say the singularities of the amplitude are, well, there are things like this, right? They factorize. Okay, so that's the statement at tree level, right? Is that clear? Right? That's what we talked about before. Now, let's say you also have loop variables, and this is now something at L loops. Okay? Well, then this will be at L1 loops here and L2 loops here. This part will look exactly the same. Just that L1 plus L2 will add up to L. Okay? But there's loops on one side, loops on the other. That just means in this diagram somewhere you have complicated loops and somewhere there's just one line going across. And we're just cutting that line. But there's another thing that can happen. Like, in this picture, I can also cut this line, right? That's a singularity where that L goes to 0, right? Now what happens when that guy goes to 0 is if I imagine summing all the diagrams, then it's as if I'm computing a tree diagram now, but with 2 extra particles in them, right? So that's the other kind of singularity. So plus something that would be at L minus 1 loops in general, but with 2 extra particles that have sort of been cut with equal and opposite momenta. Okay, so sometimes we draw it like this, sometimes we draw it like that. Okay? So that's the general kind of singularity. That's a general feature that these rational functions have to have now. Now when we retreat to talking about the loop integrands, we have well-defined objects that are rational functions, and what it means for them to be legal, what it means for them to have a local and unitary interpretation is that they should have poles where they factorize like that, and they should have poles where they don't factorize into 2 pieces, but with 1 piece and 2 extra lines that are glued to itself. Right? Yes?
What about shifting the momentum?
Very good, very good. So I was just about to come to this point. So One thing that you can ask is whether this notion of a loop integrand is even well-defined. Okay? So we can start with this guy here, and already here, just at a single diagram, there's a question of what you mean by L, right? But that's not so much of a problem. Whatever you mean by L, you can shift it or not. If the shifted L, whenever the shifted L squared goes to 0, or any one of them goes to 0, that's an invariant statement. However you label it, wherever in your L space or L prime space, wherever it happens, there's somewhere where that thing squared goes to 0. At that point, it needs to do this. Okay, so diagram by diagram, this is not a problem. A much bigger problem is if it makes sense to combine different diagrams with the same label L. Like, let's say you have very different diagrams. How do you know whether the L you mean for this diagram is the L you mean for a different diagram? How do you know how to line them all up and put them under a common integral sign, right? This is actually a very interesting question. And it turns out that in theories where all the diagrams are planar, there is a canonical way of labeling L so that what you mean by L is the same in every diagram. A very simple exercise. I won't prove it for you here. So actually, you haven't seen it before. It's a very useful thing to go try and show it for yourself. Basically, because planarity gives you a notion of L is that loop momentum between particle 1 and 2. Okay, because 1 and 2 are always drawn in the same order going around on the outside. And if the diagrams are planar, then that's a well-defined notion of L. Okay, there's more or less, there's much more elegant ways of saying it, but that most lowbrow way of saying it actually works. Okay? So if you're only summing planar diagrams, there's a well-defined notion of the loop integrand. Okay? If you do not have planar diagrams, there is not an obvious notion of the loop integrand until we begin talking about surfaceology tomorrow or on Wednesday, as things are going. Okay? Where a canonical notion reemerges, but with an interesting twist. Okay? But so far, this notion of a loop integrand makes sense in planar theories. Okay? Theories where the graphs are planar. And when we talk about color in a moment, there's some physics justification for when that is the case. Okay? So the notion of a loop integrand is available for planar theories. When it's available, this is the ultimate thing that we're looking for. Okay? So if you have any kind of machine that generates rational functions of momenta and loop momenta with this magic feature that the only poles are when this happens and where that happens, and all the poles it factorizes like this or like that, congratulations, you've built a theory that deserves to be called physics. Right? One way of building such a theory is called Feynman diagrams. Right? And we're trying to look for other ways of building theories like this. And we're going to be doing it by finding geometric spaces, positive geometries, that reflect that in their boundary structure. Okay, so that formula there really is boundary. The boundary of these positive geometries look like products of lower positive geometries and other positive geometries with this two extra lines cut in this way. Okay? Let me just pause at this point to see if there's any questions. Yes?
This looks a little like degenerating Riemann surface.
Absolutely. So that's just exactly what I was going to say, is that these equations are seen everywhere. Okay? So if you're a physicist, you see this equation everywhere. This is called the Hamilton-Jacobi equation. If you're a classical physicist, this is also the Hamilton-Jacobi equation if you're solving the Schrodinger equation in quantum mechanics. It's called the Baetzlin-Velikovsky, whatever the fuck they're called, formalism, right? They're everywhere. Okay, so we see this exactly in the boundary structure of Riemann surfaces. Okay, so exactly. In fact, I'm so glad you said this because I was debating whether to talk about this now, but I'll talk about it now. You see, imagine that but experimentalists who've maybe measured tree amplitudes, somehow has access to the loop integrand. You don't know about Feynman diagrams, you don't know about anything, but you're moving the dials, and you discover, wow, my rational functions have these poles and these places, and they factorize, and they do this, and you come to the conference and you announce, this is the system I'm studying, it does this. Please tell me, theorists in the audience, what's going on, right? And of course, Feynman's in the audience and says, what's going on is Feynman diagrams that I just named after me, right? That, because that just makes this happen, right? But if you're Pierre Deline or Mumford in the audience, you say, I don't know what you're talking about, Feynman, but I've seen this before too, right? This is exactly, for example, this top line is what happens in the very, very simplest moduli space in the world of endpoints on the boundary of a disk. Okay, so if we have endpoints on P1, so let's just look at this top line. Right, so if we have like, let's say 4 points on the boundary of a disk, well, those of you who've seen this know it, but those of you who don't are in for a treat. Okay, so if you have 4 points on the boundary of a disk, modulo Mobius transformations, modulo SL2 transformations. If you don't want to think about Mobius transformations, literally think about them as vectors, right? So you have like vectors. Two-dimensional vectors. So this is the non-projective way of thinking about things. Just think about a configuration of 4 vectors, okay? But they're ordered in this way. Say 1, 2, 3, 4, right? Now you can ask, what does the sort of boundaries of this space look like? Well, they're ordered in some way. So clearly you'll say, well, there's a boundary where like 3 and 4 collide with each other, right? So here's a boundary where 3 and 4 are nearly on top of each other. Aha, that's a boundary. But people's 3 and 4 will say, no, we're not colliding. I'm free to do a linear transformation, right? I'm free to do a linear transformation where I put these back wherever the heck I want. So 3 and 4 are going to go there. But what happens when I do that? 1 and 2 will collide with each other, right? So you can think about it now with 1 and 2 very close to each other. Okay? So the correct way to think about the boundary of this space is that the boundary is not where 3 or 4 collide or 1 and 2 collide, but the boundary of this space is this famous bubbling picture, where you think that they're sort of in 1-2 world. There's 1 and 2 sort of far apart, but 3 and 4 squash on top of each other there. That x represents 3 and 4 squash on top of each other. And for the perspective of 3 and 4, the other way, right? All right? Okay? And that's what happens in general. For any n, you can just bubble the space into 2 pieces with this kind of point in the middle that represents the entire rest of the world squashed on top of each other, right? That's remarkable, right? That's exactly what this picture is doing. Okay, so if you're Pierre Deline in the audience, you say, I don't know what you're talking about, Feynman, but whatever the heck this experimentalist is seeing must have something to do with that. Okay? And in fact, there is a picture of the world where that is the star of the show. It is known as string theory. Right? That's a picture of the string world sheet. The entire purpose of string theory is to give you a dictionary between this primitive fact about the moduli space. You see, the moduli space factorizes. That's a fact. There's a dictionary that converts that fact into a statement of poles of an amplitude that factorize. Okay? That dictionary is known as textbook string theory. And some avatar of Carolina's talk tomorrow may talk about this, or may not. I'm not sure. But anyway, but it'll be related to some of the things that she talks about tomorrow about the associahedron. Okay, so, but the point I want to make is, if factorization is the star of the show, we've had for 50 years, 60 years almost, sort of 2 pictures of the world that take this fact and build a kind of theory on top of it. One of them is Feynman diagrams. The other one's string theory. They're different. Okay? But there are 2 ways of seeing some mathematical structure that does this. Okay?
So there's some duality between the 2.
That's right, and they're closely related to each other in the end. That's sort of, in the end, we understand that these are not as far away from the Feynman picture as you might have originally thought. Okay? But indeed, what's going on in the sort of positive geometry program is the discovery of many more objects of this type. So I think that's the novelty. We have these 2 for like 50 years, and now we're seeing a bunch more. And the way they connect involves a different dictionary, right? The way that perturbative string theory connects, well, you have to read Green, Schwartz, and Witten or Polchinski for 200 pages and then start doing calculations, right? Here there's some geometry in the canonical form, and poof, poof, poof. You sort of very quickly see what the connection is between the geometries and the amplitudes. Yes?
Excuse me, talking about the string theory, if I add the adjective topological string theory,
yes.
I know that the partition function of topological string theories are quite related with differential equations as integral systems like KdV or KT equation.
Yes, yes.
And in your talk, I mean, the analytic behavior of the amplitudes is remembering a lot. Like
absolutely. I mean, look, this is what I was saying. I mean, if we wanted to, we could spend hours and hours talking about all the systems that are kind of analogous, right? And all the systems where this is going on, right? This is going on really everywhere. I mean, it's, again, this is one of those statements is either deep or content-free, or close to both, okay? But I think it's sort of no exaggeration to say this is most of physics, is this statement. Because this is, roughly speaking, the statement that the world is complicated but is made of simple pieces. And it's made of simple pieces. If you just add this is classical physics. If you add this, it's quantum mechanics, right? That's really the sort of the sort of sense in which if we have objects that kind of are built out of simpler objects in some canonical way, which is reflected in the fact that more complicated objects split into lower objects in some canonical way as you approach their boundaries. This is a kind of a universal thing that's going on all over the place. The novelty, as I just said, the novelty here is seeing a different set of objects that are doing this, and it's somehow a much simpler setting, a much more austere setting, a much simpler setting than you would have naively expected. And the sort of dictionary for converting the setting into physics is something sort of very, very instant. There's not much formalism associated with it. Just this notion of a simple notion of a canonical form kind of takes the geometric spaces that do this and immediately converts them to functions that have the corresponding properties. Okay? Yes.
So does this positive geometry that is the reverse of the question that you're asking enforces local locality in a space-time?
Yes, that's what we're going to see. I haven't told you what these objects are or where they come from, but that will be the magic when we get there. Is we're going to do something. For example, when we talk about the amplituhedron, after some preparatory remarks, we'll start talking about triangles, polygons, and we'll just ask how triangles and polygons can generalize into Grassmannians, which will motivate in various ways. And then the way that they do it will just tell us where the faces, where the boundaries of this geometry are, and they'll precisely correspond to local poles. Without putting it in by hand. I mean, they'll just sort of come out of the space. They'll come out of this, of the existence of an ordering and positivity, right? And again, you know, if you're familiar with the story of the positive Grassmannian, this is less shocking, because the positive Grassmannian is already extremely shocking to me. That you just take k by n matrices, nothing going on, boring k by n matrices. You say the columns are ordered. Okay, fine. Columns are ordered. Very good. Ordered k by n matrices with all determinants positive. Okay, well, I guess that's the sort of thing mathematicians like. Sure, let's look at all ordered minus positive. Then poof, all of a sudden this incredible structure, it's controlled by affine permutations and Playbit graphs, and all this sort of structure comes out of seemingly almost nothing. You just say k by n matrices, ordering, positivity, poof, all this stuff comes out, right? Well, we're just sort of generalizing that, okay? It's really sort of generalizing that, but the poof, something that comes out will be locality and unitarity, is what's going to come out of that. Okay? That's that story of the amplituhedron. And then when we start again with a different kind of kinematic space that's built out of pairs of particles rather than single particles, we'll get the story of curves on surfaces, which will connect to string theory in some interesting ways. But again, from a very sort of primitive starting point, very elementary and primitive starting point. But yeah, we have not seen any of the magic yet. I've just been making claims so far, but that's where we're going. Yes, you had another question.
Yeah, just you have, I mean, you are mentioning different quantities, like single, pairs, infinite. Can you make a clear connection between them?
Sorry, say again?
You have mentioned different quantities, single, pairs, as
the only thing I mentioned is that there's two kinds of kinematic space we'll be dealing with. One of them are fundamentally where the kinematics are labeled by single particles, and the other one where they're labeled by dot products of pairs of amount of pairs of particles. Okay.
And at some point you mentioned infinite number.
No. Oh, sorry. The third lecture, which is probably not going to happen now, but anyway, we'll see. The third lecture will be about something else. Will be about this is a formalism and a way of thinking about these scattering amplitudes. But in all the cases, it's not just a way. It's not just some. It's not a. You know, it's not a cosmetic thing where you just say it in a pretty way. it exposes features of these objects that we could not see before. That's the sort of most important and interesting thing about them. There's like there's hidden symmetries, sometimes infinite hidden symmetries. There's the ridiculous simplicity we already talked about. The ridiculous simplicity will become obvious in many cases. And you get access to regimes which we didn't know how to access before. And one of those regimes is the one I mentioned, where the number of particles goes to infinity. Okay? And that's associated with a totally new set of ideas that I want to, that I'm hoping that we'll get to, maybe in the last hour of these lectures.
Thank
okay?
you.
All right, any other questions? Okay, well, we have 15 minutes to go for today. And let's see what we should do. I don't want to rush anything. Let me actually stop again. Are there any questions? Yes. Yes. Yeah. I think if there's questions, I think it's a good use of our last 13 minutes to have questions. Yes.
I'm wrong, but there is some relationship between these kind of the factorization and topological recursion. If you do that.
Very much so. Very much so. Again, yes. So, well, we could spend 13 minutes, but if we start doing it, we'll probably spend 2 hours just listing all the places this kind of formula shows up. Topological recursion is very much where such formula shows up. I mean, most of the interesting things are finding the precise senses in which this formula is true. Okay, and the precise dictionary that converts them to physical quantities. Okay, so that's I think what's the most interesting thing in the story we're going to talk about is that there are simple geometric spaces that have kind of ab initio definitions that don't know anything about this, right? It's just some word, some space, something is positive, blah blah blah, and then you discover that it does this. Okay, that a little bit like the endpoints on the boundary of a disk. This doesn't know manifestly about that. It just turns out to have that property. Okay? And secondly, that the dictionary that converts it to physical quantities is so simple. It's just this form. There's a form with logarithmic singularities on the boundary of the space. That is the object that sort of turns it into a physics. That's so it's both things that are going to be interesting. Maybe I can mention something, which is one of the. I was going to mention this as an open problem thinking about the amplituhedron, but one of the amusing things which has happened is that, for example, in fact, in all of the stories, both the story of the amplituhedron as well as the story of curves on surfaces, have the sort of funny feature that the case of relevance to physics is not the top of the food chain. Okay? So what I mean is, again, this is part of the chauvinism of the theoretical physicist, is that if you run into some mathematical structure, probably the version that's related to nature, or at least related to n equals 4 super Yang Mills or to string theory, will be the boss, will be the best one. And then everything else will sort of descend from that in some way. And this is not what's going on in these stories at all, in a kind of disturbing way. Okay? So for instance, in the story of the amplituhedron, what connects to n equals 4 super Yang Mills scattering amplitudes is m equals 4. Totally weirdo intermediate case. It's not n equals 1 or even m equals 2. It's m equals 4, some random small even integer. What about all the other m, right? And all the other m are very interesting objects. And even when you loosely think about what this means for them, they generalize this in kind of a radical way. Okay? So they generalize these pictures so that, for example, you don't factorize into 2. You can factorize into 3, 4, more complicated pieces. For example, even n equals 6 appears to have the feature that the factorization is not associated with factoring into 2, but associated instead into taking a random cubic tree, take a random cubic graph, and that's a picture of factorization. You take a random cubic graph and then you sort of decorate it with blobs. In the same way here that you just take a straight line and you decorate it with blobs on 2 sides. Okay? So if you take higher m amplituhedra, they seem to give you objects that generalize these notions of factorization. Okay? On the face of it, that means that these are objects mathematically that are generalizing our usual notions of space-time and quantum mechanics. And what's so fascinating about that is that theorists have tried for ages to find any kind of extension of quantum mechanics. There's nothing. Okay? You can't mess around with quantum mechanics in any way that doesn't completely blow up in your face instantly. but they've never tried to do it while at the same time messing with the notion of space-time. Okay? And so that's what's going on in this story. Maybe I should have made this point even earlier on. Let's forget about this much more exotic comment that I'm making now. This formula, even the top line, even at tree level, it should kind of strike you. Because normally we think about, we can have theories that have Lorentz invariants, theories that have space-time symmetries. We can have quantum mechanics without Lorentz invariants. Space-time and quantum mechanics are not related to each other. We can have the classical physics that's Lorentz invariant without quantum mechanics. We can have non-relativistic quantum mechanical theories. These are unrelated concepts. Not only that, quantum mechanics and Lorentz invariants seem to, in front of the scenes, fight each other. Okay, so it's difficult to make things that are simultaneously relativistic and quantum mechanical at the same time. That's part of the great rigidity of quantum field theory, is to make things that are simultaneously compatible with both principles. But it's also very interesting that somehow behind the scenes they're very cooperative. And this is one of the ways you see the cooperation. It's fascinating that relativity and quantum mechanics show up in the same spot in the amplitudes. They're not like in different places. They're just about the pole structure. Where are the poles and what do you do on the poles? Okay? So they could have been utterly unrelated things, but they're in fact exactly the same thing, right? They're really exactly about the analytic structure of the amplitudes. And so sort of whatever the ideas are that give rise to this picture in some ab initio way, you can go back and sort of read them as a way of giving rise to some notion of locality and some notion of unitarity. Okay? When we think about how string theory does this at the level of pictures, no problem. It doesn't seem to have anything to do with Feynman diagrams, but in the end of the day, the dictionary that converts it to physics involves a conventional picture of a quantum mechanical theory that lives on the world sheet. So that's why it's not such a dramatic notion of some kind of emergence of quantum mechanics or space-time, because they're more or less there in the picture when we finally understand where it comes from in the textbook way of thinking about string theory. On the other hand, you might find other ways of getting this picture that are much further away from that, and that'll give you some sort of picture of where these notions could come from, again, further away from that. And what's interesting about these new ways of doing things is that they suggest generalizations of this picture. Okay, so whatever the generalizations of this picture are, you're invited, if you're very adventurous, to think about them as some new notion of space-time that goes along with this new notion of quantum mechanics. Okay? And that's something that's there in the amplituhedron story, because the physical case is in some rando intermediate place at n equals 4. And it's also there in the curves on surfaces story, which I'll talk about later, where that entire story sits inside a much larger world that's quite a bit more abstract and which doesn't have any of the conventional connections to, again, this kind of picture, generalizes this kind of picture in interesting ways as well. So I think that's maybe another one of the purely mathematical novelties. As you've said, we've seen this kind of thing everywhere in both physics and mathematics. But now we're seeing cases not only where these emerge in a way that connects to physics, but which suggest generalizations that are not artificial. They're sort of there in the same world of objects. So in the case of amplituhedra, it's studying higher M amplituhedra, for example.
Sorry?
Yes?
You said that positive geometry enforces the locality and unitarity principle.
Yes.
What about the reverse?
Well, that's the very large number of euros question. Okay, so we don't know. Certainly, but since we don't know, we don't have definitely the suite of theories we understand so far in this way is minuscule compared to all the theories that are out there. Okay, they're getting larger. So there are more realistic theories are being described in this language, but we're nowhere near describing, for example, all the particles and forces that we know in the standard model. Maybe, I don't know, 20% of them can be described in this language now. Okay, so not zero, but definitely not all of them. Crucially, theories without color cannot yet be described in this language. Okay, so and that's a real biggie. I mean, that's photons don't have color, gravity doesn't have color, so we don't know how to describe theories like that in this language yet. There are some hints in the surfaceology picture that we might be able to do it, but nothing concrete yet. But I think it's more the other way. There is no, the way I see it, this kind of crazy hidden simplicity, symmetries, all this miraculous properties of amplitudes did not have to exist. That's one thing that did not have to exist. They exist. Also, these objects did not have to exist. I mean, they're also not sort of just sitting around on the surface. You're sort of, you have to look for them. You have to believe they exist and look for them. But you look for them, you dig for 5 years, and you find them, right? So I don't think they had to exist. The fact that they exist and they're somehow related to the remarkable properties of the functions, I think means something. But does it mean that we're thinking about it in the correct way? Is it just a tiny part of something much different? Who knows? Absolutely possible. Yeah, absolutely possible. I just think of it as an example of kind of an existence proof that these ideas could come from somewhere else. That they don't have to essentially be there behind the scenes, as we've been seeing so far.
Thank you.
Yes.
Well, in strings here, you actually have some dimension 10 or 26 or whatever.
Yes.
Yes, here it seems that space-time dimension 4 naturally comes out because of the nature of the singularities. There are the singularities of the green function of the Laplacian in dimension 4.
Yes, so the nature of the singularities is actually dimension agnostic because the inverse of the Laplacian in any number of dimensions is 1 over p squared. Okay, so that's not special to 4 dimensions. There is something special about 4 dimensions related to the story of the amplituhedron. What's special about 4 dimensions, and this is what I'll start with tomorrow. What's special about 4 dimensions is that the space-time symmetries in 4 dimensions are, well, SO3, 1. We have Lorentz invariance as SO3, 1. Famously, SO3, 1 is also SU2 cross SU2, or really SL2 cross SL2 or SL2C. If you complexify everything, it's SL2 cross SL2. So this is something that people have known since 1930, Van der Waals and whoever. People have known this for ages and ages, right? The space-time symmetries in 4 dimensions are SL2 cross SL2. If you have massless particles, you have conformal invariance. Conformal invariance is an even bigger symmetry. It's not so visible in the Lagrangian, but it's an even bigger symmetry that, again, in 4 dimensions is SL4. So there's something peculiar that in 4 dimensions, the fundamental symmetries of space-time look like these SLs. They look like linear transformations. What the hell, right? They don't look like linear transformations in general dimensions. They only look like linear transformations in 4 dimensions. That's why in 4 dimensions, Grassmannians show up all over the place. Because everything is about these linear vector spaces. The symmetries are these GLs, GL2s, GL4 if you have conformal symmetry, right? The Grassmannians are just sort of hiding behind the scenes everywhere. And that's why the story of the positive Grassmannian, amplituhedron, et cetera, are crucially dependent on that connection. Okay? When I say that the amplituhedron can be generalized to higher M, it would be a system that has an SLM symmetry. See, in 4 dimensions, it's SL4. And SL4 is the conformal group in 4 dimensions. In higher dimensions, the conformal group is SL nothing. So when we go to like SL6, we're not doing conventional field theory anymore. We're doing something different. Okay? And as we're discovering that something different is this crazy thing that generalizes factorization and the location of factorization in the unitary in some way. So it's presumably not a normal theory. It's definitely not a normal theory. It's going to have its own weird notion of space-time. Its weird notion of space-time with distance doesn't depend on pairs of points, but on triples of points and more complicated things like that, for example. So there is a generalization to higher dimensions, but it's not our higher dimensions. It's not sort of bigger Poincare symmetries. It's something totally different. The story of curves on surfaces is totally dimension agnostic. Okay? And so it works in any number of dimensions. And the fact that we run into 10 and 26 dimensions, even the 10 of the 26 can be relaxed in interesting ways because we're not literally doing string theory in that picture, as we'll discuss when we get there. But yeah, but the specific, I mean, you could imagine that there is that just like the amplituhedron in 4 dimensions is about the space of the individual momenta, but somehow to see all the structure, we had to go to the space on which the symmetries act linearly, right? Could there be some picture in 6, 8, 10 dimensions, normal dimensions, which treats the momenta one at a time and discovers some sort of positive geometry in that space? Perhaps there is. I would be fascinated to find it. I don't know what it is yet. But yeah, so the story of the amplituhedron is about 4 dimensions. The story about curves on surfaces that we'll talk about later will be about any number of dimensions.